Hey there, and welcome. Sometimes just counting things, 1, 2, 3, just doesn't cut it for describing the real world. Today, we're going to dive into the numbers that let us talk about things like debt, or freezing cold temperatures, and, well, a whole lot more. So let's jump right in.
Here's our game plan. We'll start with why we even need these new kinds of numbers. Then we'll create a map to visualize them. After that, we'll figure out how to compare them, master the rules for how they work together, and finally, we'll see why any of this actually matters in your day-to-day life.
All right, so our first big idea is about moving beyond simple counting.
Think about it. How do you write down that you owe a friend $5? Or that it's 10 degrees below zero outside? The positive numbers we all learned as kids, well, they just don't have an answer for that. We need a new tool in our toolbox.
And that tool is simply the idea of positive and negative. We use a plus sign for the good stuff, the gains, like getting 4 new members, and we use a minus sign for the losses, like 5 members leaving. It's such a simple but really powerful way to show opposite ideas.
Now, this whole big family of numbers we're talking about has a proper name. They're called rational numbers. And the main idea is super simple. If you can write a number as a fraction, it's rational. That even includes a whole number like 3, right? Because 3 is just 3 over 1. This is the big universe of numbers we're playing in today.
And inside this big rational family, there's a special group we're going to focus on called the integers. These are your solid whole numbers, positive, negative, and 0. No messy fractions or decimals allowed. Everything else, like 1/2 or negative 0.2, they're still rational, just not integers.
So if we crack open the integers, you'll see they have 3 parts. You've got all the positives, which are just our regular old counting numbers. You have their mirror images, the negatives, and sitting right in the middle, you have 0. And 0 is special. It's totally neutral, neither positive nor negative. It's our home base. Okay, so now we know what these numbers are. But how do we organize them so they make sense? Well, for that, we need a map. And our map is the number line. This line is our absolute best friend for understanding integers. You've got 0 right in the center. That's the origin. All the positive numbers line up to the right, getting bigger and bigger. And all the negative numbers head off to the left. It's the perfect way to see everything laid out. Now, a really cool thing we can do with this map is measure distance. A number's distance from 0 is called its absolute value. And here's the key. It's not about which direction you went, left or right. It's just about how many steps you took to get away from 0. So let's make this real. If you're standing on the number line at -3, how many steps does it take to walk back to 0? It's 3 steps. Simple as that. In math, we use these 2 little vertical bars to show we're talking about absolute value. So the absolute value of -3 is just 3. And what's really cool is the absolute value of +3 is also 3, because they're both the exact same distance from our starting point.
So here's the one thing you have to remember, the golden rule. Because absolute value is just a distance, it can never, ever be negative. It's always going to be 0 or some positive number. That's it.
All right, we've got our map. Now let's use it to figure out how these numbers stack up against each other. Who's bigger, who's smaller?
The rules start out pretty easy. Anything positive is bigger than 0. Anything negative is smaller. And with 2 positive numbers, well, the bigger number wins, obviously. But here's the twist, the one you got to watch out for. When you compare 2 negative numbers, the one with the bigger absolute value is actually the smaller number. Kind of weird, right?
And this is exactly why that number line is so useful. Just forget all those rules for a second and remember this one simple fact. Any number to the right on the line is always greater than any number to its left. That's why -3 is actually bigger than -6, because it's to the right on our map.
And now for the main event. How do we actually do math with these numbers? Let's get into the rules for adding, subtracting, multiplying, and dividing.
Okay, let's start with adding numbers with different signs, like -5 plus +2. Here's how it works. First, just ignore the signs and find the difference between the numbers. So 5 minus 2 is 3. Easy. For the last step, you just look back at the original numbers. Which one was further from 0? The -5, right? So our answer takes its sign. The answer is -3.
Now, subtraction has this amazing little secret. Ready? Instead of ever subtracting a number, you just add its opposite. So taking away a +2 is the exact same thing as adding a -2. And once you do that little flip, you're just doing addition. And we already know how to do that. It's a total game changer.
You'll love this. For multiplication and division, the rules are even easier. There's a really simple pattern.
If the signs are the same, so 2 positives or 2 negatives, your answer is always positive. If the signs are different, your answer is always negative. That's it. Those 2 rules work for both multiplying and dividing.
So we've gone through all these rules, but why? Why does any of this matter? Let's bring it all back to the real world.
Let's put this all together. Imagine you borrow $5 from a friend. Your balance is now -5. But then you sell 2 things for $4 each. That's a gain of $8. So where are you at? You have -5 plus +8. Using our rule, the difference is 3 and the bigger number was +8. So your new balance is +$3. See? Those rules just helped you figure out your finances.
And it goes way beyond just pocket money. These exact same rules are the bedrock of banking systems tracking your money, of scientists measuring temperatures or electrical charges, and even how computer programmers write the code that runs pretty much everything.
So, we've seen how rational numbers and integers all fit into this really neat, orderly system. But that leaves us with one last, really fascinating question. What about a number like pi? You know, 3.14159, and it just goes on forever, never repeating. You can't write it as a simple fraction. It doesn't seem to fit our rules. So, where on earth does it belong? Well, that is a story for another explainer. Thanks for joining me.